H plus ion, the solution will be a basic solution and the pH will be greater than 7. So acids and bases are free H plus and OH minus ions respectively. Then this is the mathematical form of your acidity. It is a mathematical form of pH, which expressed as pH equal to minus logarithm base 10 of H plus ion concentration. Okay, and you also write as minus log base 10 S3O plus ion. It is also correct. And this bracket, that is the square bracket, it indicates the concentration of H plus ion in molarity. That means it is your moles per liter. That is number of moles of solute present per liter of solution. It is known as molarity. So this will be minus log S plus or S3O plus ion concentration. Operational definition, this is not needed. Then, uh, then by using Nernst equation, yesterday we have gone through Nernst equation, that is E equal to E0 cell minus 0.0591 by N log product by reactant. Okay, if it is minus, product by reactant. If it is plus, it will be reactant by product. So, if I expressed the Nernst equation in terms of your pH, then according to that equation, pH will be E cell minus E0. That E cell minus E0 cell divided by 0.0591. This will be the equation where E0 is constant because it is a standard state, and it is constant that is different from for the different cells. This is the principle involved in your pH metry or pH metry analysis. When the pair of electrode or combined electrode, and here we may use glass electrode and calomel electrode. Calomel electrode contain mercury in mercurous chloride. That will be calomel electrode. It is dipped in aqueous medium. A potential is developed across the thin glass of the bulb, that is the glass electrode. And the EMF, or that is the electromotive force, that is the cell potential. It is formed by linking these two electrode at a given temperature, and is therefore the net E cell equal to E reference minus E. E reference is your calomel electrode. That is standard calomel electrode SCE, standard calomel electrode potential, minus the potential of the glass electrode. It will be the net cell potential, uh, uh, net cell potential between the reference electrode and the glass electrode connected. So E reference is the potential of the standard calomel, which is plus 0.25 volt, 0.25 volt, and the electrode potential of glass is the potential of the glass electrode, which depend on the pH of the solution under test. The resultant EMF can be recorded potentiometrically by using vacuum tube amplifier. Variation of pH with E, that is the net cell potential. Variation of pH with E may be recorded directly on the potentiometer scale graduated to read the pH. So this will be the variation of pH, that is that we will measure through the pH meter, and the what is the cell potential we have recorded, that will be highlighted. So it is very much easy here that two electrodes are used here, glass electrode and reference electrode. A reference electrode is our standard calomel electrode. It has the cell potential of 0.25 volt. Okay, and the glass electrode we have used, the change in electrode potential of the glass electrode, it depends on the change in pH, and which is recorded through the potentiometer, which which is a digital instrument. Electrode in pH determination, for finding the pH of the solution, one should use an electrode reversible to H plus ions. The glass electrode, which is reversible to H plus ion, is the most commonly used as indicator electrode. So here glass electrode is used as indicator, which has the application of reversibility of H plus ion. Generally, calomel electrode is a reference. The most widely used ion selective electrode is the glass pH electrode, which utilizes a thin glass membrane that is responsive to change in H activity. So this is the thin glass membrane used in the glass electrode is sensitivity. It's sensitive to the change in pH of the solution. So by following this principle, we are able to find out the potential difference through the change in pH. So these are again highlighted here the important components. Glass electrode, that is indicator electrode here. Calomel electrode is the it is your reference electrode. There is standard calomel electrode that is 0.25 volt. It has the potential. Then we have electrometer which or voltameter. It will indicate the change in potential. So first one, glass electrode is consist of a thin bulb about 0.1 millimeter thick, blown on a hard glass tube of high resistance. Okay, so this is the construction of your glass electrode. The bulb contains 0.1 moles per liter HCl connected to a platinum wire via silver chloride combination. So the bulb, which is 0.1 millimeter thick in the glass electrode, contain the zero point 0.1 molar of hydrochloric acid with platinum wire via your silver chloride combination. Then calomel, we have discussed this one in our yesterday's class, that it contains it contains mercurous chloride with KCl. And the change in KCl, or the concentration of change in KCl, concentration change, um, has a direct effect on your potential difference. So these things you should remember, that in calomel electrode we have the change in concentration of KCl. Then electrometer, this is a very small difference in electrode potential will be traced or will be noted through a device, that is electrometer. Their working mechanism: an acidic medium or acidic solution has far more positively charged hydrogen ion than an alkali, so it has greater potential to produce an electric current in a certain situation. In other words, it is a bit like a battery that can produce a greater voltage. A pH meter takes advantage of this and works like a voltmeter. It measures the voltage produced by the solution. So here in pH metry, in the container, we use an acidic solution that will produce large amount of H plus ion as with respect to the alkaline or OH minus ion concentration. And this H plus ion will has the advantage to have greater cell potential to generate greater cell potential difference, which will be highlighted or noted through the pH meter. When two electrodes, glass electrode and calomel electrode, are dipped in solution, some of the hydrogen in the solution move towards glass electrode and replace some of the metal ion in the special glass coating. This creates a tiny voltage across the glass to silver electrode picks up and passes to the voltmeter. Reference electrode acts as a baseline or reference for the measurement. So the role of reference electrode is only to standardize the instrument, that is the baseline or the reference, that is the that cross check the instrument, that the instrument is okay or not before our experiment. So here what happened, the solution which we have put in the in the cell will react with or has an effect towards the glass electrode, and which is consist of the silver chloride cell. So that's why the change in potential will be highlighted in the voltameter. A voltameter measures the voltage generated by the solution and display it as a pH measurement. So the change in voltage displays it as a pH change. An increase in voltage, this is the increase in voltage, means more H plus and less OH minus, and the solution is acidic and a pH will be down. So when the solution becomes acidic, there will be more H plus ion. If there is more H plus ion, the voltage or the potential difference will be high. And the reverse may also happen, that if the voltage is downs or decreases, there will be less H plus ion and more OH minus ion. The acidity will be decreased and the pH will increase. So these are the just vice versa, or they are just reverse things. So by this process, we will correlate the pH with the potential change, that is in voltage. So just remember, in pH symmetry we have two types of electrodes are used, that is glass electrode and your standard calomel electrode. Glass electrode is acts as indicator electrode, and calomel electrode is acts as the reference or standard electrode. And the cell potential or the electrode potential of your your calomel electrode, that is standard calomel electrode, is 0.25 volt, and the glass electrode, that is the indicator electrode, consists of a thin glass of 0.1 millimeter thickness with your silver chloride precipitate, and a platinum wire is there. Okay, a bulb is there which contain platinum wire and with silver chloride solution. Then if we change the pH, or if we pass the solution, then if the voltage rises, the net voltage in the electrometer or voltameter is increases, then we conclude that the solution is highly acidic and which contain more number of H plus and less number of OH minus and the pH will be less. If the pH is more, then the voltage will be less and this will be inversely proportional. Then a glass pH electrode, the most widely used glass pH electrode measurement, that is selective ion in H plus. The response is fast. This is stable, has a broad range. pH changes by 1 when H plus ion changes by a factor of 10, and potential difference is 0.05196 volt when H plus ion changes a factor by 10. For a change in pH from 3 to 6, potential difference is 3 into this, that is 0.177 volt. So this will be the mathematical things you should remember, that for every 1 unit change in pH, the potential change will be 0.05. It is actually 0.0591. It is 1, not 19. This is 91. So for every 1 unit change in pH, the potential difference change will be 0.0591. Okay. Then pH glass electrode, it is thin glass membrane. This is just a bulb like, which is consist of silicon tetroxide. Most common composition is silicon dioxide, and this is sodium oxide and calcium oxide. Glass membrane contain dilute HCl solution, inbuilt reference electrode, silver wire coated with silver chloride. So in many cases, platinum wire is also used, and yeah, in the glass membrane which consist of a bulb, contain a silverware that coated with silver chloride precipitate or salt. Any equilibrium establishes across the glass membrane with respect to H plus in inner and outer solution. This produces the potential E, linearity between pH and potential, calibration plot, yield slow 50 millivolt per pH unit, and electrode is prevented from drying out by storing in aqueous solution when not in use. So these are the things that is precaution we should take. What are the advantages of using glass electrode in pH metry? Now, this is used in solution with pH value from 1 to 20 range, and a lithium glass electrode can be used to measure up to 14. Well suited for continuous automatic recording and control of industrial and commercial processes, and permits rapid measurement, simple to operate, used for both oxidizing and reducing solutions, doesn't affect solution under examination, can be used in colored, turbid and colloidal solution. So these are the advantages or positive factors of a glass electrode which is used in our pH metry analysis. What are the disadvantages? Due to high resistance, ordinary potentiometer cannot be used. These have high resistance in solution of protein and other colloids, and that tends to adhere to the sensitive membrane. The glass electron may yield erroneous result, cannot be used in acid fluoride solution because in acid fluoride there will be presence of S plus ion and F minus ion, and F minus ion has more has okay. So H plus ion and F minus ion will be there in acid fluoride, which the fluoride ion, the F minus ion has more reactivity, which may interfere uh, in the measurement of the pH and voltage. That's why in acidic fluoride solution, this method cannot be used. And if it is strong alkaline solution, there will be less number of H plus ion and more number of OH minus ion. And at that condition also, this glass electrode doesn't perform well. Cannot be used at high temperature for prolonged period due to partial dehydration of glass electrode. When used in non-aqueous medium, it cannot be employed to measure pH in that medium. So these are the disadvantages. So some of the disadvantages you should remember for your examination point of view. Two types of pH meters are there. That is potentiometric pH meter, that is slide ware, which we have already discussed, and direct reading type. So combination of pH electrode, that is majority of pH electrode available commercially are combination electrode that are both H plus sensitive and additional reference electrode. Okay, so these are the commercially available pH electrodes. The glass electrode and calomel electrode can be constructed together in a single probe called combined or combination electrode. So nowadays, two separate electrodes are not in a pH metry or pH meter instrument, and these two are now combined, and we have only one electrode that acted as a dual electrode, that is it both perform as calomel electrode as well as your glass electrode. The combination of pH electrode measure the difference in potential between the two sides of the glass electrode. To measure the potential, there must be a closed circuit. The circuit is closed through the internal solution of the electrode and the external solution that is being measured and the pH meter. So these are the just the advantages of your combined or combination electrode. As the electrode is immersed in the solution, the glass bulb senses the H plus ion in millivolt due to positive charge of the H plus ion. The electrolyte or internal solution pick up the millivolt signal from the glass tube, glass bulb. That signal is then passed to the internal electrode. And the electrode that contains silver chloride wire coated with silver chloride passes the signal to the electrode cable that leads to the electrometer or voltmeter. So these are the chains which passes the signal from one to another. That the first, the S plus ion signaling the glass tube. The glass tube is then the internal electrode. Internal electrode contains silver chloride, which passes the information to the electrometer or galvan or your voltmeter. The reference electrode contain electrolyte or filling solution generates a constant millivolt potential, which is transferred to silver sulfide wire. And the reference electrode will also generate 0.25 volt. The wire is then passes the signal, which can be considered a control being measured by the electrode cable. So these things happen, and at the end we have the circuit which grows by minute amount of internal solution from the reference electrode flowing through a porous membrane made of ceramic wick. The membrane or junction, as it is called called, is located at the electrode body. The pH meter measures the difference between the internal electrode and the reference electrode in millivolt in direct current. This millivolt reading is then read by the voltmeter or electrometer and displayed in pH unit. Okay. So by with the variation of your voltage, the potential difference, the pH is measured. How the pH is changes. For or how what is the pH of a particular solution through your pH meter. So this is a pH meter instrument, and here the reference electrolyte filling here, that is your um, mercury in mercurious chloride, and a KCl potassium chloride, and this is the reference electrode element, that is mercury. Reference electrolyte here, that is KCl, and a reference junction here, and pH sensitive glass tube bulb. This is the glass bulb, which is made up of silicon tetroxide or silicon oxide or sodium oxide, and it contain a platinum wire or silver wire that is coated with silver chloride. Okay, this one. This is the glass electrode, contains silver in silver chloride, and this is the filling hole cover. This is the cover just, and this is the pH meter. Okay, just by dipping this instrument in our solution, and we will able to know the pH of the solution through the potential difference arises between the reference calomel electrode or standard calomel electrode and the glass electrode. So this is nowadays a very common instrument in various research labs or chemistry labs, and by using this instrument we're able to find, or we're able to know the pH of an unknown solution without taking much time. Okay, so this is a very fast instrument, and the complete cell will be, the what is the complete cell will be, this is the glass electrode, that is silver in silver chloride, and HCl is there because the bulb contains 0.1 molar HCl. So this will be the oxidizing part, and the reverse part will be the calomel electrode, that will be KCl in the mercurous chloride and mercury. The glass electron, calomel electron dipped in a solution of known pH. Then the net difference or net cell potential will be the reference electrode potential minus the glass electrode potential. So what is the equation? That is again, we will obey the Nernst equation. That will be delta E equal to 2.303, and this is delta E means it is equal to that means E delta E equal to your E cell minus your standard, that is E0 cell, that is delta E. It is equal to 2.303 at T by F, pH of 2 minus pH of 1. So this is just your so pH of 2 minus pH of 1 means it is the first pH of your solution and standard solution, and this is the pH of your unknown solution, pH of 2 minus pH of 1. Then This is the setting of your pH metric. The CO, this is the glass electrode, this is the calomel electrode, and this is the glass electrode, this is the bulb, and here silver is coated with silver chloride, and here your mercury and mercurous chloride. It's wrongly written here. This is Hg2Cl2, and it is the saturated solution of KCl. This is sample under test. So by dipping this instrument in the solution, we have the voltmeter. Here it is how the potential changes. The glass electron must be soaked in. The glass electrode, this one, must be soaked in 0.1 molar HCl for 24 hours, followed by storing in distilled water. The electrode result in the pH range 2 to 10 and up to 14 with a special glass. Then we have advantages. If handled properly, it can be used for long time. Can be used in the presence of strong oxidants and reductants in various media, and in the presence of protein, and mostly equilibrium is reached quickly. Disadvantages: direct reading cannot be taken due to high electrical resistance potential, hence amplification of the signal becomes necessary. Then, uh, then the thing that is the what is buffer, and buffer is a solution which pH doesn't change significantly when small amount of acid, alkali or base or water is added to it. That means it is a solution which pH doesn't change. Because after the addition of small amount of acid, alkali or water to it. This is known as buffer solution. And our blood, which has the pH of 7.4, blood has the pH of 7.4, and it acts as a buffer solution in our body. That if we take slight excess of acid or slight excess of alkali or base to uh, in our body, then it will not change the pH of the blood, because it will adjust to the blood as blood is acts as a buffer solution. So buffer are the solution which pH doesn't change. Okay, after addition of acid, base or water to it. So buffer are the solution that have constant pH and the ability to resist resist change in pH. They are used to calibrate the pH meter, and buffer are the solutions which are used to calibrate. That means before using the pH meter to unknown solution, we should calibrate or standardize the pH meter by using a buffer solution, which pH is already known to us. Before measuring pH, we have to calibrate the electrode. To calibrate electrode, we need at least two solutions of known pH. Most commonly used buffers are pH 4.01, 7, and 10. So these are the things we should understand, and we should remember that before using the pH meter or pH metric analysis, we should standardize or calibrate the instrument using a known standard of buffer, and generally 4.01 pH, 7 pH or 10 pH buffer is used for its standardization or calibration. So the next step is to put electrode into pH of 7 buffer. Then rinse the electrode with distilled water from a wash bottle into an empty beaker before immersing into a new solution. That means you will take distilled water in a beaker and immerse the electrode, and then after after noting the pH that is equal to 7, then you put the same electrode to your new solution, which pH is to be determined. You should do it every time electrode is moved from one solution to another, to minimize the contamination. Check if the working part of the electrode is completely immersed in the buffer. This is very important, that the working part should be completely immersed. Take care to not hit bottom of the beaker with the electrode. This is just a hanging type, and it should not be touch the bottom of the beaker. Wait for the reading to stabilize, and after stabilization of the reading, you should note it down. Then next step will depend on the solution you want to measure the pH. If you plan to measure pH in acidic, then you should use the buffer like 4.01 buffer. If you wish to measure the pH of a basic or a alkaline solution, then you should use the buffer 10.0. So if you want to be able to measure pH in the wide range, you may want to proceed with 3-point calibration. You will need both buffers. So it depends which type of solution you wish to measure the pH. And if your solution is a acidic solution, if you have the information that it is an acidic solution, measure its pH. So just you should go for the buffer solution for 4.01 buffer for standardization. If you have a solution of alkaline medium or basic medium, you should use 10.0 buffer pH. Then if you are not have the information that the solution is neither acidic or basic, or you are confused after putting after with the taste of litmus paper, that it can either be blue color for alkaline or red color for acid. If you have any confusion, or if you do not have any information, then you should make it such a type that to calibrate the instrument uh, in all the three buffers, that is 4.01 and 7 and 10.0. Remember that high pH buffer tends to absorb atmospheric CO2, thus they should be used as fresh as possible. Do not leave the bottom bottle open, and do not calibrate and do the calibration immediately after filling the beaker with the buffer. So this is just a precautionary step that if you have the high pH buffer, it will absorb carbon dioxide. So it should not be open, and it should be the calibration should be done immediately. The accuracy of pH measurement by using pH depends on external factors like temperature, pressure. The electrode had to be calibrated. We cannot have accurate values. Application of pH to measure the biological fluids like blood, urine, gastric acid, etc. to ascertain type of biological condition, useful in determination of concentration of substances by pH measurement, to know pH of buffer solution, to maintain pH of reaction condition, to measure the pH of soil, which will be helpful in maximizing the yield and return from the soil, to measure the pH of rainwater, maintaining perfect and accurate pH level in several daily activities like keeping the milk from turning sour, pH meter employed in chemical industries, neutralization of effluent in steel, pulp, paper, pharmaceutical manufacturing, biotechnology and petrochemical industries, helps in analyzing the exact pH value of chemical substances and food grade product, thus ensuring high level of safety and quality. So this is nowadays it is a common instrument or common apparatus, you can say, which is used for the determination of pH or and in different fields. And at the end, this will be the end of our pH metric. Okay, so you should remember what is pH, the concept of pH, that is mathematical form, how acidic and alkaline or basic medium are defined by pH, and how the pH meter construction, what is its instrumentation, and the detail about the different components, that is standard electrode taken, that is standard calomel electrode as the reference electrode, followed by your indicator electrode as the glass electrode, which contained a glass bulb which is made up of silicon tetroxide, contain zero point 0.1 molar HCl with silver wire in silver with coated with silver chloride. And we have calomel electrode contain mercury with mercurous chloride and potassium chloride solution of different concentration. So by connecting these two electrodes and with the external circuit, we have connected a voltmeter or electrometer. So by variation of voltage, if the voltage downs or decreases, we mm, we predict that pH is more, and if voltage is more, pH will be less, and if pH will be less or decreases, that indicates the solution is an acidic solution, and if pH increases, it indicates that the solution is an alkaline or basic medium. And these are the application advantages, disadvantages, and various advantages of your glass electrode. And you may face some problems. You may face some problems related to your pH by using your mathematical equation, that is pH equal to minus logarithm of H3O plus or H plus ion concentration. And you should remember, if the pH of a solution is, let us, it is pH equal to 3, that means pOH of that solution, the same solution, will be 14 minus 3 equal to 11. That means if a solution is with a pH of 3 has the pOH value of 11, that will be 14 minus 3, that is 11, and if it is neutral, it will be 7. So for pH metry, we have discussed all the sections very in elaborately. And if you students have any doubt or anything else you want to ask related to pH metry, you may ask, and after that we will move towards conductometry titration in our next unit, that is unit 4. So is there any question or anything else you want to add or you want to ask? Over to you, students. Any question? Mahendra, Chandini, Mahadev, Akarsan, Rajasmita, Somnath, Anil, then we have Mahadev Mandol, Nagesh, Nazrul, Ojas, Ranjan, Rohini, Somnath. So total of 16 participants or are joined today. So if no questions are there, we may take 5 minutes of break here, and we will move. We will have unit 4 in our next part of discussion. That is conductometric titration. This one we have conductometry in our next part. Okay. So till then, let's have some refreshment. Then we will come back. Okay. Thank you. Welcome back, students. Am I audible to you all?
Yes, sir.
Yes, sir.
Okay, thank you, thank you, thank you. So do not worry about the PowerPoint presentations that I have presented, and I will like our previous paper. After completion of the all the units, I will share all the PDFs in your WhatsApp group. Okay, and you may read that PDF for your theory examination. Then we have this one. I think it is shared and it is visible to you all. Is it visible now? The
Yes, sir. Yes, sir.
conductometric iteration. Okay, wait, wait. What happened? Okay. So this is conductometry. So conductometry means it is very much clear that it is related to conductance. So in pH metry, that is related to potentiometry. That in that part we have gone through the potential. That is the potential difference that is in volt. And here it is the conductance. What is conductance? Conductance is the it is a property of a substance which allows the flow of electron or flow of heat through a substance, or in a scientific definition, it is the ease with which a substance conduct electricity or heat through it. That is known as conductance. So as we know, conductance is the reciprocal of your resistance. So resistance is just which resist the flow of heat or electricity, and according to the relation, the conductance is denoted as G and resistance is R. That means G is equal to 1 by R. So there is one Ohm's law is there. So the unit of resistance is ohm and unit of conductance is G. So in this part we will have the unit that is conductance. Okay, and let's have some introduction. It is an electrochemical method which is concerned with the electrical conductance through an electrolyte solution. So what is electrolyte solution? Electrolyte solution, it is what is electrolyte? Now uh, when it is added to a solvent, the electrolyte when it is added to a solvent, it forms an electrolyte solution in which the electrolyte is dissociated or ionizes to their respective ions. That is known as electrolyte. So electrolyte is again of two types. There is ionic electrolyte and non-ionic electrolyte. So ionic electrolyte means it will produce both the ions in the medium. For non-electrolyte, it will not ionizes and it will remain as a whole molecule in the solution. So these are known as for example, in our first class, the yesterday class, I already mentioned that in copper electrode is dipped in copper sulfate electrolyte. That means what? Copper sulfate is an electrolyte which ionizes or dissociated in the medium, aqueous medium, as copper 2 plus ion and SO4 2 minus ion. That means it is an ionic electrolyte. Okay, electrolyte solution. So in this method we will concern with electrical conductance through an electrolyte solution, and it is defined as determination or measurement of electrical conductance of an electrolyte solution by means of conductometer. And here the instrument is known as conductometer. And in potential analysis we have potentiometer. If it is pH, it is known as pH meter or pH metry. And the electrolyte electric conductivity depends on type of ion, concentration of ions, temperature and mobility. So these four on these four parts the electrical conductivity depends. Then these are the basic things. We have already discussed these things in our first part. Let's have some overview of these parameters in your electrochemistry or electrochemical analysis. And this is the Ohm's law, that is I equal to V by R. I is the current, V is the voltage or cell potential divided by resistance. So what is resistance? It is the it is the power of a substance or which resists the flow of electricity, or which opposes the flow of electricity, and this is reciprocal, or it is equal to inverse of conductance 1 by G. What is specific resistance? Specific resistance is, okay, so specific resistance is, it is a resistance offered by unit length and having unit cross sectional area, that is R proportional to L by A. So what is conductance? It is the each with which current flows per unit area of conductor per unit potential applied, and is reciprocal of resistance, that is G. Specific conductance is K. It is the conductance of a body that uniform length and uniform area of cross section. Then these are the parameters you should remember, and remember that a specific conductance equal to conductance into cell constant. Here it is not written that specific conductance equal to conductance into cell constant. Just remember this equation, that specific conductance equal to conductance into cell constant. Then your PDF is good, I think. So this is electrolytic conductance cell. Yes, these are electrolytes and non-electrolytes. So electrolytes, we have ionization in electrolytes. For example, sodium chloride, potassium chloride, this will give positive ion and negative ion in aqueous medium. So these are electrolytes. So electrolytes is again of two types, strong electrolyte and weak electrolyte. Strong electrolyte, why these are strong? Because these are ionizes completely, or there is 100% ionization. 100% ionization. So that's why this is known as strong electrolyte. And similarly, there will be weak electrolytes are there. In weak electrolyte, just wait, student. Okay. So in weak electrolyte, there is incomplete dissociation or partial dissociation will happen. For example, if I take sodium chloride in aqueous medium, then sodium chloride will dissociate completely. There is 100% dissociation. So these are strong electrolyte. So in weak electrolyte case, if we take this is your acetic acid. If I take acetic acid in aqueous medium, it will not dissociate completely. There will be no 100% dissociation. So this is known as the weak electrolyte. Okay, and whatever non-electrolyte means this will not dissociate at the medium in which it is put. Okay, so non-electrolytes are like cane sugar, benzene, carbon tetrachloride. This will remain as a whole molecule in the solvent. So that's why this is non-electrolyte. Then we have the same thing. This is conductance G 1 by R. So R unit is ohm. The G unit will be ohm inverse. Then again, this is the Ohm's law. I equal to E by R, or I equal to E into G. Then we have, this is the resistance, which is directly proportional to length of the cell and direct inversely proportional to area of cross section. So this is the sorry, length. No, this is not the length of the cell. This is the distance between the two cells. Sorry. So this is L, and this is inversely proportional to area of cross section, L. So R equal proportional to L by A, and R equal to rho L by A, where rho is known as the specific resistance. So how to define the specific resistance rho? So it is otherwise known as resistivity. So specific resistance rho resistivity is defined as the resistance offered by a solution or a material in which the distance is 1 unit and area of cross section is 1 unit square. That means it becomes 1 by 1. That means R equal to rho. So specific resistance becomes your resistance. Okay. So in mathematical form, rho equal to R A by L. So what will be a unit? R equal to ohm. It is your centimeter square by centimeter. It will be cancelled. So ohm into centimeter. It is your unit of your rho. That is resistivity or specific resistance. Similarly, for your conductance, it will be 1 by R. So for R, we have written rho A by L. So 1 by rho, this becomes your K, that is kappa. It is known as kappa, K. It is known as a specific conductance or conductivity. It is specific conductance into A by L. Okay. So conductance equal to specific conductance into A by L, where A by L is known as the cell constant, and it is equal to centimeter square by centimeter. It will be centimeter. So these are the things you should remember. That is K cell equal to L by A. This is a cell constant, and it will be centimeter by centimeter square. It will be centimeter inverse. The unit of cell constant is centimeter inverse. Then this is specific conductance into cell constant. I have written here specific conductance into cell constant. So conductance is ohm inverse, cell constant is centimeter inverse. So specific conductance unit will be ohm inverse into centimeter inverse. Okay. Then we have the next part, molar conductivity. Molar conductivity means the concentration of the solution which conductance is to be measured is 1 molar concentration. That if I take 1 molar concentration and the conductance offered by that solution is known as molar conductance. Okay, that means molar conductivity or molar conductance is the conductance offered by all the ions present in that solution with 1 molar concentration. Okay, then we have the formula, that is molar conductance is denoted by lambda m. Lambda m equal to K by C, where K is known as the specific conductance kappa divided by C, that is in concentration, that is molarity. So this will be Siemens into meter square into mole inverse, or Siemens into centimeter square into mole inverse. These are the units of your molar conductivity. Then concentration equal to molarity into 1000, that is per liter. So so next is our equivalent conductance, that is symbolized as lambda eq. So it is the conductance offered by a solution having 1 gram equivalent or equivalent of solutes. So the formula is lambda eq, that is equivalent conductance. It is equal to 1000 into K by C, where C is the concentration in normality. And in molar conductance, it is in molarity, moles per liter. In equivalent conductance, it is normality. What is normality? Normality is when 1 gram equivalent of solute present per liter of solution. It is known as one normal solution, and the unit is known as normality unit. So the unit of equivalent conductivity or equivalent conductance is ohm minus 1 or ohm inverse centimeter square equivalent inverse. Okay, you should remember the units. These are very important things. That is for K, it is ohm inverse centimeter square, and for your concentration it is equivalent inverse, because it is in the denominator part. That's why it is equivalent inverse. So that means equivalent conductance means it is the normality, and if it is molar conductance, it is the molarity. Molarity means moles per liter. Equivalent or normality means it is equivalent mass per liter. Okay, these things you should remember. So variation of conductance with concentration, and just remember with dilution. With concentration means what? The concentration varies. How the concentration varies? If we make it diluted, the concentration will vary. So with the dilution, both the molar conductance as well as the equivalent conductance will decreases or downs, because the number of ion per unit volume decreases. This is very important. This is number of ions per unit volume. Okay, so if I diluted, if I add water to a definite solution, if I take 1 molar solution and find out what is its molar conductivity, and then I add 1 liter of water, then what happens? The volume increases to 2 liter, and the number of ion per volume will decrease. If number of ion per volume will decrease, then simultaneously what happen? The conductance will decreases. So the same thing is for your equivalent conductance, that is it will decreases when when we make it more diluted. And if we change the concentration to higher level, that is for 1 molar concentration, the conductance is conductance, let us it is equal to 7 ohm inverse. Then what will be the conductance for your 2 molar solution? It will double, 14 ohm inverse. So these things will be there. That with dilution it will decreases, and with concentration if increases, the conductance will also increases. This is the let us see this table. For 1 molar, for KCl it is 111.9. For NaCl, it is 106. The molar conductivity of electrolyte in aqueous solution at 298 Kelvin. And if the molarity 0.1, it is 129.0, 106.7, and so on. So just read out this one. The conductivity of an ionic solution increases with the increase in concentration. It is written here. The conductivity. And here, the specific conductance are here, I think. For strong electrolyte, the increase in conductivity with increase in concentration is sharp. However, for weak electrolytes, there will be two electrolytes are there, strong and weak. The increase in conductivity is more gradual. In both, someone is unmuted. Who is he or she? Ranjan Sharma.
Yeah, hello, Prakash sir.
Just wait, just wait.
Hello.
Actually, some noises are coming in. Okay, Ranjan, please tell.
Yeah. Sorry to interrupt you. Actually, your voice is quite too low, and plus background noise were there. I think
Okay, okay.
now
Now,
it's
now,
clear.
now it is okay.
Now it is clear. Yeah.
Okay, thank you, thank you, thank you. So it is the variation of conductance with concentration. How the conductance varies with change in concentration. So it is just remember, we have two types of electrolytes: strong electrolyte and weak electrolyte. So for the conductivity of an ionic solution increases with increase in concentration, and for strong electrolytes, the conductivity increases with increasing change in concentration is very sharp, because for strong electrolytes, what happens? There will be a cent percent or 100%, or these are dissociated completely. So that's why the ionic mobility will be more, and the conductance will be more. However, for weak electrolyte, The change in conductivity, it is also increases as the concentration increases, but is very more gradual. Gradual means it is very slowly it will rise, because for weak electrolyte what happen, there will be partial dissociation. Okay, these things will be there, and you should remember these things depends on the ions per unit volume. This is very important. So if I change the volume, if I make it more diluted, the number of ion per unit volume will decreases, and the ionic mobility will decrease, because the volume increases, the distance increases, the mobility will be downs. If the mobility will be downs, the conductance will also downs. Then we have this plot is there. This is for your strong electrolyte, and this is for your weak electrolyte. Just wait. Hello. Okay. Hello. Namaskar. So then we have the plot between concentration with our conductance. If it is molar conductance or equivalent conductance, then we have this type of plot for your strong electrolyte KCl, and this type of, this is gradual downs in equivalent conductance with dilution. This is for your acetic acid, that is a weak electrolyte, that is on dilution, it is written here on dilution. Okay, on dilution both strong electrolyte and weak electrolyte, the conductance will decreases. So the one cause is that number of ions per volume decreases. That's why the, if ions decreases, the conductance will definitely decrease. Then we have limiting molar conductivity. This is an important relation which can be obtained by extrapolating the curve for strong electrolyte. This is, if I extrapolate this curve for strong electrolyte with dilution, then this line will be collide with this zero line. Okay, this will intersect here. Then after intersection, what happened? This is known as limiting molar conductivity. So the limiting molar conductivity, if concentration tends to zero, where interionic effects are absent, the limiting value obtained by this extrapolation is called molar conductivity at infinite dilution. The dilution will be infinite, that is strong electrolyte conductance becomes zero. That means there will be negligible number of ions per unit volume. Their ionic mobility is decreases considerably. That's why the molar conductivity decreases, or it becomes very low, very less. So this at this condition, this molar conductivity is known as limiting molar conductivity. So the formula is limiting molar conductivity will be conductivity as infinite dilution minus some constant b into root over of c. So this will be the equation for limiting molar conductivity. Lambda m, the molar conductance, equal to conductance at infinite dilution minus some constant b into root over of c. So just go through these things, and this is the lambda infinity equal to lambda infinity plus lambda infinity minus. This is just related to your this is at infinite dilution. Okay, there is one law is there, that is known as I will say. Okay, so these are the things you should go through these things. Then ionic mobility and transport number. So So how what is the mathematical form of ionic mobility and what is transport number? So transport number, the mobility of an ion in solution mainly depend on the size of the hydrated ion. Size of the hydrated ion means what? If it is a small ion, it will be largely hydrated. If it is a big ion, it will be less hydrated. So um, the less hydrated ions will move, the ionic mobility will be higher than for a small ion which is largely hydrated. So this will be the there will be factor that is hydrated ion. This will be that is it is the sorry, hello. So then we have this is the limiting molar ionic conductivity lambda infinity. It is for your positive ion. It will be Z plus U plus F, where Z plus Z minus are the valencies, U plus U minus are the ionic mobilities, and F is the Faraday. So you have to remember this equation. That is molar conductivity at infinite dilution for respective ion equal to the valency, it is ionic mobility and into Faraday. And there is another quantity that is known as transport number or transference number, which is indicated by T plus and T minus. It is defined as the fraction of total current carried by ion species and is expressed mathematically as this. That means it is the fraction of current. The total current passed through a solution is 10 ampere. So how much current is carried by positive ion and how much current is carried by the negative ion with respect to the total ion. This is known as the transport number. So transport number, it is denoted as T plus and T minus. So T plus equal to lambda plus infinity by lambda n. It is the conductance and infinite dilution by molar conductance, and T minus is lambda minus infinity by lambda m. So this is the thing. It is your transport number, and always remember T plus and T minus. If we sum up these two, T plus T minus, it will be always equal to 1. There will be unit ampere or unit current pass through this, and these are the values, limiting ionic mobility values, and this will have the reactions or movement of H plus ion through water. These are the things. Then effect of other factors on conductivity like temperature effect and pressure effect. And if temperature rises, the ionic mobility will rise. If ionic mobility will rise, the conductance will increases. And pressure has less, slightly slight effect on conductivity. The conductivity increases slightly with it increase in pressure. The effect is mainly through change in viscosity of the medium. If viscosity changes, the effect is mainly happen with decrease by increase in pressure. The effect of solvent is there. In solvents of low dielectric constant having a small ionic ionizing effect on the electrolyte, the electrostatic force of forces between oppositely charged ion would be appreciable, and equivalent conductors will have small values. So this is effect of solvent. Effect of medium is there, which is we have a equation that Walden rule, that is infinite dilution conductance and infinite dilution into a constant, that is that is it is equal to n0 equal to constant, where n0 it is known as the coefficient of viscosity. Okay. So how to measure electrolytic conductance? We have the principle, that is Wheatstone bridge principle. We read this one in our class 11 12 level in physics. We have 4 registers combined connected in series, and we have a conductometer here, we have a key here, and this is the power supply. Okay, then these are the mathematical form, that is R1 by R. This is R1. It is known resistance. This is R2 known resistance. R3 is also known, but Rx is not known to us. So this is the equation R1 by R3 equal to R2 by Rx. Just see here. This is R1 by R3. These two series connection equal to R2 by Rx. Then we have Rx equal to R2 R3 by R1. So here G, the conductance G equal to R1 by R2 into R3. If resistance is this one, conductance will be the reverse. That means R1 by R2 into R3. This will be the Wheatstone bridge. Just go through these things, and also you should remember this diagram. Measurement of conductance solution. So these are the things we should follow the principle of Wheatstone bridge. There will be direct current would polarize the electron in the conductivity cell by electrolyzing the solution after polarization, and a suitable conductivity cell is located between C and D. Let's go through this one. These are very much easy things. Okay. Then we have the next part is conductometer. This is the conductometer instrument. We just this instrument is having the frequency range of 50 to 1000 range, and we would and like Wheatstone bridge, we follow the principle that inverse of resistance is conductance, and we directly read on a conductivity measurement instrument, that is the conductometer. So conductivity conductance is directly measured by this instrument, which is known as conductometer. Okay. So these are the cells used in conductometer. That is, various cells type cell have been designed and are in used for the measurement of conductance of a solution. There are Pyrex glasses. Pyrex is just like a company, the reliable company. Pyrex glass. It is very costly, fitted with electrode of platinum or gold to overcome the imperfection in the current and other effect. The electrode are coated with a layer of finely divided platinum black. This is achieved by electrolyzing 3% solution. Let's have our PPT for instrumentation. Yes, yes. These are made up of Pyrex or quartz glass, are fitted with two platinum electrodes. There are two platinum electrodes, or in your PDF it is written gold is also can be used, because these are the noble metals, and they conduct electricity. Water in to maintain constant temperature. Type 1 wide mouth cell, cell for reaction producing precipitation. Wide mouth cell is measurement of low conductance. Wide mouth fitted with an ebonite cover, which has provision for platinum electrode and borates. Mainly used for a precipitation reaction. I pronounce it as PowerPoint. It is not PowerPoint. It is precipitation. Also, wide mouth fitted with ebonite cover, which has previous provisions for burette electrode and stator. Stator may be mechanical or magnetic. These are the electrode used. Platinum sheet. These are dimension. This is surface coated with platinum black. Platinized electrode is turned with coating with 3% chlor platinic acid. Chloroplatinic acid is not chloroplatinic acid, and lead acetate ion on it to get uniform coating. Electrode uses depend on conductivity and concentration. If concentration is low, then electrode should be largely and closely packed. Then this is a diagram of electrolytic cell. This is a diagram of, no, we have the PTF here, and this is the thing that this typical design of conductivity cell here. That is, it is mainly of two electrodes. That is platinum. Okay, and we have a stirrer here. This is magnetic. This is manual stirrer. That it will be, the solution should be stirred. Then we have the procedure here. First, plug the instrument, put the frequency as required. Then calibration should be done. That is the standardization. Then we have connectivity. Connect the conductivity cell electrode to appropriate terminal of the instrument. It depends. Then take the potassium chloride solution 0.1 molar in clean beaker. This is a standardization. Okay. Introduce stirrer and put the solution behind magnetic stirrer plate. Insert the conductivity cell in a solution. Ensure the platinum plate electrode are completely immersed in the solution. They do not touch the stirrer rod or the side of the bottom. This is very important. Do not touch the bottom. Switch the instrument and warm and leave it to one for 2 to 5 minutes. Measure the conductance G of standard. This is GS. This is for 0.1 molar KCl. GS for standard, and putting meter switch to read. So first you switch to CAL, that is calibration, and after calibration you just switch off to READ, read. Then put the same electrode in your unknown sample and get the result. Then Ks will be conductivity of the standard divided by observed conductance, that is Ks by Gs. So K of unknown sample is equal to K cell into Gu. That is conductance of unknown sample. So by multiplying the K cell and Gu, you will get the conductivity, that is a specific conductivity of the unknown sample. So these are the applications of your conductivity cell, that it can a conductivity measurement. This can be used for estimation of purity of distilled water. Yes, yes, that equation is known as Collard's equation, that infinite equation, that at infinite dilution the conductance offered by the respective ions will be the total conductance offered by the respective ions will be sum of the conductance offered by the positive and negative ions. This type of principle is there. That is a lambda infinity equal to lambda plus infinity plus a lambda minus infinity. This is a Collard's law. Okay. So application, the second application is your finding the moisture content of the soil. Then it is your conductance and resistance of a solution. If it is a type of diatrimetric reaction with EVDA, this type of for this type of redox reaction also conductometry approach may be used. Then these are the, just go through these things, and these are the applications of your conductometry titration. Okay, so this is just a instrument. So first step is calibration with 0.1 molar KCl. Then second thing we is put the same electrode to the unknown sample, and by using this equation you are able to find the specific conductance. Okay, so this is all about for today's class, that is unit 3 and 4, related to your pH metry and conductimetry. And tomorrow we will have the class on the next part will be your electrograviometric, and your unit 5 will be electrocoulometry, and followed by your amperometry. These things are there. So so I think the class is over today. For today's I have some work. Okay, so that's why the class is ended here. And if any questions are there in today's class, we will clarify it in tomorrow's or next class. We will have tomorrow, I think. Tomorrow there will be no class, and Monday we will have classes. So thank you, students, and I will share all the PPTs. Do not worry about that. Okay. Thank you.
Sir, sir, Prakash, sir.
Ranjan, Ranjan. Yes, yes.
Sir, Saturday and Sunday, can you take classes, sir? because we are working and it's very difficult for
Eh,
me.
actually, your classes are recorded by the IGNO Delhi.
No,
So they have holidays on Saturday and Sunday.
that
So
they,
that's why there will be no classes. This is the schedule, na? Yes, there will be no classes on 19th and 20th because this is Saturday and Sunday.
so we understood it, but I think earlier
Eh,
sir has.
we may conduct the class, but that class will not be taken as official.
I don't know, sir, but I think previous sir has taken our class on, I think, the holiday day also. He has requested to director and he has taken the classes. Because
Okay, okay,
actually, it's very
okay.
difficult for me to, maybe for others also. At 5:30 a.m., actually, I used to drive back to home, and it's very
Yes, yes,
difficult to
yes, yes,
attend the
yes. I
classes
understood.
at
I understood the
5:30.
problem. Okay, I will talk to the coordinator, and after that, if it is possible, I will put a message in your WhatsApp group. Okay, then we will take the class.
Okay.
Okay, so thank you to all. If any query or questions related to today's session, we will clarify it in our next session. So thank you to all.
Thank you, sir.
Thank you, sir.